Hybrid search optimization in OpenSearch. What is the best hybrid search configuration for your application? This is a question users may struggle with. So we set off to build a couple of notebooks that have the aim to support users find the ideal hybrid search optimization through automated experimentation. I will run you through a couple of notebooks that we built together that are all available by release of this video in a public repository. Maybe the state of the notebooks has changed, but the general idea behind the notebooks will still be the same. Let's start with the basics, preparing OpenSearch so that you are able to actually use machine learning models inside and run hybrid search queries. We are using a plain vanilla OpenSearch installation. In this case, it's version 2.16, but everything that we are doing will also work with more recent versions. So let's get started. We assume that we have OpenSearch running at localhost port 9200. We're starting out with a couple of imports, and in that case I won't run every cell, so everything is prepared, but you can see the output of the runs here. So when you follow along and get all the notebooks, you can see everything accordingly in your local installation. So first we configure the ML Commons plugin. What we need to do is we need to apply a so-called cluster setting. In this case, it's a very simple put command that we send to OpenSearch, and if everything goes well, we get back acknowledged true, so that worked out. Next, we need to register a model group. So this is basically how OpenSearch organizes models internally. And once we have a model group registered, we need to get the registered model group ID. So we can actually now register one model in this group. So registering a model group again is a post command, a very simple one that you are seeing here. We are registering a model group named MLP model group, but you can choose whatever you want. And we are retrieving the set model group ID and store it in a variable here so we can use it in the next cell. What needs to be made sure of is, so we need to have this status created, which then gives us the assurance that everything worked out and we have one model group registered. Now we only have a model group but no actual model, so the next step is to register a model in this model group. We're using an all mini-LM L6 v2 model, which is one of several options that you can choose within OpenSearch. Of course, this set of notebooks deals with hybrid search optimization, but not really with choosing the best model for you. So choosing the best model may be a set of separate experiments for you that you need to conduct. We are assuming that you already know what a suitable model is for your application, and we are using in this example the all mini LM L6 v2 model. So what we are doing is again a post request by referring to this model that is available for your use in OpenSearch. This may take a while because this now means that you need to download the model and make it available within OpenSearch. So running through that code will take maybe a couple of seconds, a couple of minutes, depending on your internet basically and where you're running this. Now once we have the model, we need to deploy it. So deploying means basically making it available on the specific OpenSearch nodes. And we can check the status of this operation, and once we get the status completed, this means that we now have the basic availability of using a model within OpenSearch, and using a model means we want to create embeddings. When using hybrid search, creating embeddings, of course, means we need to create embeddings during indexing time. So we need to transform the data into embeddings when storing them in the index. We also need to create embeddings during query time by using the same model so that we can, well, compare apples to apples, right? So that's what we can test after having deployed and registered this model, and we can do so by using the predict endpoint of the ML Commons plugin. So in this case, you see that we are using calling the model ID that was just deployed up here, and we can now define a string and tell the predict endpoint that we want to have the sentence embedding for this. And when we send this request to OpenSearch, we get back the sentence embedding, which is basically an array of a lot of floats. So this is now our, let's say, assurance, the definite answer that we have now a model that is working as expected in terms of we can now calculate or generate embeddings for strings. What we need now is we need an ingest pipeline that takes parts of the documents that we index and then creates embeddings based on these documents that we send to OpenSearch. And we can do so by creating an ingest pipeline. This ingest pipeline now has a processor, and this is a text embedding processor that now takes the product title field of any incoming document and generates a field called title embedding by sending the product title to the model and receiving the sentence embedding and storing the sentence embedding in this title embedding field. So now we only have created this ingest pipeline, and now we are basically ready to use this OpenSearch installation by really ingesting and indexing data, which is what Notebook 2 covers. So, switching to Notebook 2, indexing product data, or in this case we're using a very specific data set, the ESCI data set. You may already know of this data set. If not, it is a large data set containing not only queries and judgments for these queries, but also product data. So what we are doing in this notebook is we assume that this data set is already available on the local machine. So in my case, you can see where I put this data set, and we are loading this data set and then indexing it. In the cell over here, you can see that we have a product ID, a product title, a product description, product bullet point, product brand, product color, and product locale. Product locale is our way of identifying, is this maybe a more Spanish product or a product in an English language. And we will focus on using only the data that has the product locale US assigned to it. So from all the products that we have in this data set, 1.8 million roughly, we select 1.2 million. So this is a fairly large data set that we are working in. We have a basic schema defined, and we now need to add information that now enables hybrid search, or specifically that enables the storage of embeddings. And embeddings is just another word for vector. So what we now add into the, let's say, basic schema that we have available in the repository is we enable the index to be a KNN index, so K nearest neighbor index. We set the created pipeline as our default pipeline, and we add into the schema also a mapping for our title embedding field and say this is now k and n vector, and it has 384 dimensions. 384 dimensions is very, let's say, very specific here, and you need to make sure that the number of dimensions here matches also the number of dimensions that the model that you have deployed into your OpenSearch cluster supports. So in our case, our mini LM model has or supports 384 dimensions, and these numbers need to match. So we now create an index with this schema. We make sure that we don't already have an index by first deleting it and then creating it with the schema that we have defined. And now we have an index called e-commerce. So in this e-commerce index we have nothing at the moment. So this means we, as a next step, want to populate the index with roughly 1.2 million documents. So we take the data frame and we create a bulk request or several bulk requests that send 1,000 documents at a time to OpenSearch. And this of course takes a couple of minutes, so that's why I use a prepared installation here. And as you can see, when we run through this, we get back feedback for every 1,000 documents that were indexed, and we can have a quick check afterwards. So how large was the data frame that we indexed and how many documents were indexed. And as you can see here, this adds up, this works. So if we say post and execute a match all query, or don't really define a query, which then is basically a match all query, we can now see that we have all these fields that we just had a look at: product bullet point, product ID, locale, color, brand, description. And you can also see the title embedding in this. So every document now has embedding based on the product title that we indexed. So that's it for now. We have prepared the OpenSearch installation. We have indexed 1.2 million documents. Next up is we want to create a baseline, which will be a keyword-only search. So we start out with a keyword-only search and then assume that this is what we now have in production. And based on this baseline, we want to identify the best hybrid search configurations. So let's have a look at the baseline search and metrics part. We create a query set and run a best match query with what we call a reasonable set of search fields and weights. We didn't do any experimentation to get to this list of search fields and weights. We just used all the search fields or the fields available in the product data and came up with, let's say, best guess of these weights to have something as a baseline that we can later then compare our ideal or found hybrid search configurations to. So how do we do that? We have already defined two data sets, or two query sets is maybe a better way of putting it. So we have a small query set and we have a larger query set. The small query set consists of 250 queries, and I will be using this throughout the remainder of these notebooks to have also an example that is easily reproducible and doesn't take ages to finish. So these data sets are all based on the ESCI data set originally. So we just did random sampling on these to come up with these small and large data sets. If you want to use the larger one, you can just change the Boolean value here to small _b equals false, and that will just use the larger data set, which contains 5,000 queries. The train test split is 80%, 20%, so we use 80% of the queries as our training data and 20% of the queries as our test data. This means that we now use the test part of this query set to come to our baseline, so we will always use 20%, 50 queries, run this test set against the configuration and then calculate metrics based on the results. What does judgment mean? A judgment is always a rating that tells us how well does a given product or document match a specific query. So in this case we now have the query 09 G6 wheel not cover gray, and then we have a document B07 WSB V4PK and a judgment of 0, and this means that this document is irrelevant for this given query. We have a graded scale 0, 1, 2, 3, 0 being irrelevant, 3 being an exact match. In between we have 1 and 2, which is, well, either more towards irrelevant or more towards relevant. And the ESCI dataset is basically the abbreviation of, is it an exact match, is it a substitute, is it something complementary, or is it irrelevant? And that's where the naming originates from. So we are now transforming the judgment data to have not these ESCI labels, but the grades, so 3, 2, 1 and 0, so that we can work with these and then have metrics calculated based on the results. As you can see here, for the queries that we have, the 250 queries, we have a varying amount of judgments per query. So for the top query here we have 39 judgments, for the next one we have 40 judgments, and so on. This also means that if we retrieve results, there is, in this case, actually a rather high likelihood that we retrieve results for which we don't have any judgments. So this is basically how we can later on measure uncertainty, how well do the experiment results that we have retrieved, that we have made, how certain are we that these are really robust or stable results. So in this case we already know there are queries with more judgments than others. Next, we put the ratings that we have, the judgments, into a specific format so that we can use them later on. And we save them because later notebooks will also use these same ratings. We don't need all the ratings of the ESCI dataset, so in this case we're basically narrowing everything down to only the queries and judgment or the query document pairs that we actually need. So only those judgments for the 250 queries that we are using throughout this example. So next we are getting into the query side. As I already said, we have a best fields query, a multi-match best fields query. We are searching in the product ID, the product bullet point, the product color, product brand, product description, product title. And as you can see, we assigned, let's say, best guess field weights to these. The title is the most important one if we don't have an ID match. Then comes the brand, then the bullet points, then the color, and then the description. We use an AND operator, meaning that all the query terms need to be present. So this also means that we may even run into zero result queries for keyword search only. And keyword search only is what we are now applying. So we are executing all the queries that we have in our test set. So 50 queries. And then we retrieve the results. We build together a data frame that stores all the relevant information that we need. And then later on we can calculate the metrics. So what are these pieces of information that we store? We have the query ID, we have the query string, we have the product ID, so the retrieved document from the index. We have the position, so top position is position 0, next one position 1, position 2, and so on. We are retrieving 10 results in our baseline. We also store how many results were retrieved, which may be an interesting piece of information later on. We store the relevance, so the score of the document calculated by OpenSearch, and also the so-called run. So run in this case default. We could have also named that baseline, whatever we choose. We just store it that way. Next, we merge the retrieved results with the ratings. So what we want to have is, for all the retrieved results, is there a rating in the judgment data of the ESCI dataset? And we can see the top 10 results, the 10 retrieved results for the first query that we're looking at right now. So this is some query about a bathroom sink drain. And you can already see that we only have one rating for this. So based on the data that we are using, we can only say to a very certain extent, is this a relevant result set or not? And as you can see in the next cell here, we do have a lot of rows in our relevance data frame, so the retrieved results, that do not contain a rating. So this makes the results somewhat uncertain that we are dealing with, but in terms of the baseline, it's the best we can get right now. So what we are doing is we are using the available data and then see how certain we are with these results and metrics that we have calculated. So calculating metrics. We are calculating 3 metrics: DCG, NDCG, and precision at 10. We have a specific an additional utils notebook that deals with this, or it's not a utils notebook, it's a Python file that has functions for the DCG, the NDCG, the precision values and metrics, and also the ratio of ratings. So the ratio of ratings tells us how many ratings are there for this query that we are looking at. We are now iterating over the data frame that we have right now, so the one containing the results and also the judgments. And we are calculating the DCG, the NDCG precision value, and the ratio of ratings for these. And now you can see for the first query, we have, after this calculation, a metric of a DCG metric or value of 1.15. The next query has one of 4.24, next one 6.5, and so on. We can now also have a look at very specific queries in here, and then see for the black bear onesie query, we have this DCG value that we already had a look at. We have an NDCG of 0.475, a precision of 0.2, and now we can also see how many ratings we had in these retrieved 10 results. So a ratio of ratings of 0.4 means we have, for 4 out of the 10 documents, we have ratings or judgments in the data set that we are working with. So 40% of judgments is not bad, it's not great, but that kind of gives us an idea of how reliable these calculated metrics are. We can now average all the different metrics and have something like an aggregated baseline value afterwards. So if we create the mean of all the 3 metrics that we are interested in, so the mean DCG, the mean NDCG, and the mean precision value, we arrive at these values over here. Note that averaging over these may not always be the best solution to really come up with an aggregate. Specifically for DCG, this may be problematic because we don't have maybe 10 perfect results for each query, making it somewhat slightly unfair to compare, let's say, an average DCG value for baseline with an average DCG of the different search configurations for hybrid search that we are exploring later on. So this is our way currently now to be able to compare baseline with different other experiments that we run throughout the set of this, throughout the set of these notebooks. Now we can also visualize these results. So maybe we want to see how well do the queries do, what's the distribution of the different metrics for the different queries calculated. So to do so, we create a pivot table for these. So now we have per query the different metrics in the columns. And when we visualize that and let's say compare the calculated DCG values with the ratio of judgments that we have per query, you can see that there is some kind of, let's say, linear correlation maybe to be seen in this graph. So the more judgments on the y-axis we have means the higher DCG values we get. So up here we have 100% of judgments and a DCG value of 18.1. And down here, 0 judgments means a DCG value of 0, of course, but there are outliers where we have a lot of judgments but low DCG values. Yeah? So this gives us the idea that if we find better configurations, we may end up with better not only sorting but more relevant results in the top 10. So this already gives us maybe a basic idea of is there something to improve? We have a lot of ratings for some of the queries but not ideal DCG values, so maybe there is something to improve here, and that's what we are going to find out in the next notebook, where we iterate over a lot of different hybrid search settings to find the ideal one for our search scenario here. So how can we find out the best hybrid search configuration? We're going to use a very straightforward approach first that iterates over a set of 66 different configurations, calculates the metrics for these based on the retrieved results, and then we compare the metrics for all of these different configurations to see which scored best. And then we have, by trial and error, basically found out the best hybrid search configuration. It's admittedly not really a very complex or very sophisticated approach, but it's a straightforward approach by just trying out in a set of given parameters all different combinations. So let's have a look at the details here. We're using the same data set, the same query set. So as you recall, in the previous notebook we loaded a small query data set that has 250 queries split into 200 train queries and 50 test queries. You also recall that we generated the ratings file, so all the different ratings from the ESCI data set for these 250 queries of our small query data set. Let's make sure we can run hybrid search. We have one model in our OpenSearch installation, so to get the correct model to use to apply when doing or executing a hybrid search, a hybrid query, we can just query our models and return 1 and get the ID of this model and store that in our model ID variable. Next, we can define a search pipeline. To define a search pipeline, we have a couple of parameters that we can set. So hybrid search works as a post processor. So this means that we run a keyword query, we run a neural query, and afterwards we mix the results by normalizing and combining the different scores the keyword query and the neural query had. So as I said, we have normalization and we have combination. So in OpenSearch, one of the normalization techniques is the min-max normalization. The other option is the L2 normalization. And then there are different combination techniques. Different means, basically: arithmetic mean, harmonic mean, and geometric mean. You can read up all the details if you want to in the OpenSearch documentation. Last but not least, we can apply a weight to the different subqueries. So one subquery the keyword query, one subquery the neural search query, and we can now say we want a more keyword heavy search executed or more neural heavy search executed. And the weights in our case will always add up to 1. So if we have a keyword weight of 0.3, we will have a neural weight of 0.7. So defining all these parameters and then putting them all into a pipeline means that we can initialize this pipeline before we run the first query, and then we can just use the pipeline and send queries to the pipeline without having to initialize all the hybrid search specific internals within OpenSearch. Once we have the pipeline, we can now use it. So we take a multi-match query that we already know from the baseline, and now we add a neural query. In this case, we want to query the title embeddings that we generated during indexing time. And once we execute this query, we see that we get hits, and these hits now have a normalized score returned. Normalized in a way that we have now a neural score, a keyword score, and they are normalized and combined to one final score that we are here seeing in this response. Of course, we're still retrieving all the different and all the already known fields, so the title, the ID, etc., etc. So this just means we are able to execute hybrid queries. Next, we want to try out all hybrid search configurations. So we know there are two normalization techniques, L2 and min-max. We know there are three combination techniques, arithmetic mean, harmonic mean, and geometric mean. And now we define 11 keyword search weights and 11 corresponding neural search weights. So we're using the weights 0, 0.1, 0.2, 0.3, 0.4, up to 1. And the other is always the corresponding value 1 minus what we have as the keyword search weight. So again, if we have a keyword search weight of 0.7, we have 1 minus 0.7 equals 0.3 as our neural search weight. We create all these different combinations, store them in a data frame, and now we have for each normalization, for each combination, for each keyword weight, corresponding vector weight, and that gives us a pipeline name. But what we won't do is actually create a pipeline for each. We will always create a temporary pipeline for each query individually. That saves us running through the pipeline creation steps in this kind of offline evaluation and experimentation scenario. So what we do next is, for every combination that we have created, 66 altogether, we will now execute all the queries that we have in our training data set. Then we retrieve the results. So our training data set is 200 queries strong. We retrieve 100 results. And based on these 100 results, we store again everything in a new data frame. And then by using the already known judgments, we can calculate metrics again. So at the end of this run, we have for all of the 200 queries executed 66 pipelines, and we have 100 results per query and pipeline combination. That gives us quite some data actually, so let's have a look what metrics we get out of that. So our relevance data frame now contains 1.3 million and 20,000 rows. That is 200 queries times 66 pipelines times 100 results. So that's how this number takes shape. Now we calculate the metrics per pipeline. Again, we're using the results that we have just received. We merge the results together with the ratings. It's the same mechanism that we had in the baseline notebook. And then we calculate the metrics. Of course, we calculate the same metrics like in the previous notebook, in the baseline notebook, to have something that is comparable. And in the resulting data frame, we now have per query and per pipeline, we have one metric. So we have the DCG metric and the value, we have the NDCG metric, the value, the precision metric and the value, and of course also our ratio of ratings, so that we know how many ratings we had per query pipeline combination in the results. We store that to make sure that we don't have to rerun everything if we want to have a second glance at the results. So this takes quite some time actually, because we have to run a lot of queries, right? So 200 queries per 66 pipelines, retrieving 100 documents, it takes some time in this local installation, and the code is not optimized for performance, I must admit. So if you want to, feel free to provide a pull request to optimize the code and maybe run things in parallel. Now, when we calculate metrics per pipeline, we can then sort in descending order and get the highest values per metric. So the best NDCG value is apparently 0.28 for a couple of pipelines, and all these pipelines, the top 5, have the L2 normalization, the arithmetic mean combination, and a keyword weight value between 0.4 and 0.8. Now, when we have a look at the DCG value, we don't have as many equal values, but 0.4 and 0.5 with L2 norm and arithmetic mean, they all have a 6.12 DCG value and also an identical precision. So these two apparently are like the best combinations that we have in terms of hybrid search configuration options. So best pipeline, you could say, is either the L2 normalization, the arithmetic mean combination, and a keyword weight of 0.4 or a keyword weight of 0.5. So more or less equally weighted with a slight preference towards neural is what our actual experiment here shows us. We need to be aware though, so we are calculating all the metrics at position 10. We only have roughly a third of the of the judgments that we would need. So we only have on average judgments for around about 3 query doc pairs per query. So this is not a lot. And this is basically our way of defining that the results that we are calculating here, the results that we are getting from these experiments, they are to some extent uncertain. So this is something we need to keep in mind, but we need to deal with the data that we have. We cannot deal with data that we don't have. So this is just something to keep in mind to know how reliable these values are that we came up with. Again, we store these results to be able to retrieve them, and of course now we can dive into some details and, for example, see for one specific query what were the results, what were the relevance scores that we retrieved, and what were the ratings, or what are the ratings that we have in our ESCI dataset. And in this case you can see there are a lot of NaNs, so unavailable ratings, unfortunately. But still, yeah, we can calculate metrics. We can calculate different metrics to maybe have different angles despite having as few. And now, as we know that the best pipeline configuration is this L2 arithmetic mean 0.4 is what we take in the next step. We can now apply this to our test data set. So with the training data set, we now calculated what is the best pipeline. And now with the test data set, we can evaluate how well this works out. So what we can keep in mind up here is this DCG value 6.12, NDCG 0.28 and precision 0.31. If we now run the 50 queries of our test set against this pipeline or this configuration arithmetic mean L2 norm and the keywordness of 0.4 and the neuralness of 0.6, again get all the results in this DF relevance test. In that case, we can again merge it. Then we have judgments and results in one data frame. We again run through the metrics calculation, again the same metrics that we had before, and now we arrive at metrics for our test data set. So the test data set scored a DCG of 6.27, an NDCG of 0.28, a precision of 0.32. And now we can compare that to the baseline. And that's what this table shows us. So the 50 test queries baseline scored an NDCG of 6.03, an NDCG of 0.26, and a precision value of 0.3. And now our global hybrid search optimizer, global in terms of we find one globally best configuration set, we can see it scores actually better than baseline. So we already have a success for this first, let's say, very broad optimization step. So we have global an DCG value for the global hybrid search optimizer step of 6.27, which is an improvement of 0.24. Not bad. We have slightly better NDCG, 0.6 versus 0.28, 0.26 versus 0.28, and slightly better precision, 0.3 versus 0.32. So already an improvement, but this is a very static approach, right? So this approach identifies a global configuration that works best across a larger set of queries. But in this larger set of queries, of course, we will have winners and losers. Yeah, on average, it scores better, but there will be ones that really benefit from this configuration, and there will be queries that don't benefit from this configuration. And in the next notebook, we'll have a look at some of these examples at least, or how we could dive into details. So in this notebook, we're going to dive into a couple of individual queries and hybrid search configurations. So what we have overall is here are our total stats. So how many query doc pairs are we looking at? That's now the test set, the training set, sorry. 200 queries, 66 pipelines, 66 hybrid search configurations, times 100 results that we retrieved. We only have a coverage of 8.3%, 8.4% across the top 100. We've seen in the pipelines when we calculate metrics at 10 that we have like 32% coverage. So it of course improves if we look at the narrower part and the top part of the result set only. So we use the results, we use the ratings, so nothing really unusual here. And again, we rerun and recalculate some of the metrics, in this case per query per pipeline, and then we can create averages. Yeah, so these are basically the numbers that we have seen before. Yeah, the 6.12 as the best DCG value is something that we've seen. The 0.28 as NDCG value is what we have already seen. So nothing new until now. We can also have a look at specific and individual queries to have a look at some of these metrics. And you can see here for one query, for example, we have a lot of zeros. Yeah? So this is, in this case, clearly related to not really bad results. We cannot tell because we have 0 ratings for example, these 5 configurations that we are seeing here. Yeah? So uncertainty, again, is a topic. So again, just sorting to have an overview of what are the best pipelines, and now we can create a couple of visualizations. So visualizations, for example, can be we want to plot the NDCG versus the DCG value. And what we see rather nicely here is that we have, I would say, linear correlation apparently. Yeah? So the higher the DCG on the x-axis is, the better the NDCG on the y-axis is. So we don't really have perfect NDCG for any, but of course this is per pipeline aggregated, not per query. So we are averaging across all queries for one pipeline, one search configuration. We can have a look at DCG versus precision as well. And we also see like this apparent linear correlation here. The higher the precision value is, the higher the DCG value is, and vice versa. NDCG correlation is not quite, NDCG versus precision, sorry, it's not quite as maybe linearly to be seen, but still you can say the higher we get for the NDCG value, the higher we also get for the precision value. Now, as we have a lot of missing judgments, we can also use maybe slightly different takes on DCG. So we can remove all the unknowns and only use the knowns, only the known judgments, and remove all the NANs. And then sum and not average per pipeline, not across, like within one query and a pipeline. And this now gets us a different view. So in this data frame here, we are looking per pipeline at the mean and also the sum over all query doc scores. And that is now, let's say, a slightly different take. And we can have a look at the ones that score best if we apply this. And we still see like the 2 winners that we have seen before. So if we create the sum DCG, so the sum over all query doc judgments, instead of creating a DCG value per query and then averaging over the queries within one pipeline, this gives us a similar picture. Yeah, so they are very similar, only different at the first digit after the period here. Now, when we create the means within all queries of one pipeline, we see a slightly different picture actually. Yeah? So the slightly different picture here prefers all the very keyword heavy pipelines. Yeah? So that's maybe an interesting twist in the story here. So depending on how we aggregate the cumulative gains that we have within a result set, we can see a different picture. Yeah? So this is something to keep in mind, but what we chose to do is, as the sum of the different individual query doc pairs gave us a very similar picture than the averages across the query-specific DCGs within one pipeline, we chose to follow that path throughout the remainder and the following notebooks. But of course, we can also have a couple of visualizations here. So this is a very nice linear correlation that says the more available judgments we have, the higher our DCG value gets if we have this, if we exclude all the NANs and sum up all the query doc cumulative gains. And I think that is pretty, let's say, that was expected from our side, because the more query doc pairs we have with judgments, the higher our score gets. That's kind of natural, and that's why we see this very, very clear and almost perfect linear correlation in this visualization. If we have a look at the mean DCG, the picture is slightly different, but the picture was also slightly different when we had a look at the aggregated metrics just a couple of seconds ago. So points are really scattered around this plot, and there's no real correlation to be seen here. And again, that led us to really dismiss this mean DCG. It also is never used in literature anywhere, as far as we know at least. So we focused on or discarded this kind of metric and only looked at other ones. So one of the last plots here, again, perfect correlation here when we average over the query DCGs, and that is again, and contrasted to the sum, that is again a very, let's say, clear distinction that if we improve on one, we also improve on the other, so linearly and almost perfectly correlated in here. And always when we have a look at the mean over the query doc DCGs, it gets scattered around without any correlation. That's why we have really discarded this view on metrics after this notebook. So the next notebook will enable us to drill down in specific queries. So let's have a look how this notebook is built. So let's drill down into single queries. We load the result sets, so the one where we have per query the different returned documents per pipeline and the ratings merged into this. We also get the different metrics that we have scored, so basically the results of the previous notebooks. Now we can, for example, have a deep dive into two pipelines that are maybe not as similar, so one that's rather keyword heavy and one that's rather neural heavy, to really see how the single and individual queries, how they behave. Yeah? So maybe we find candidates that perform very well in one case or not so well in the other case. So having a look at the first couple of queries here, and we can zoom into specific ones. So maybe the 100% success without college is an interesting one, because we have in the keyword heavy setting a DCG of 4, and in the more neural search setting or neural search heavy setting, we have a DCG of almost 7. Yeah? So that would be an indicator that for this kind of query, we have we would benefit from more neuralness than keywordness. But there definitely also are examples that point rather in the other direction. So sometimes keyword heavy is better than neural search heavy. We are not seeing any example in this view here, but trust me, there are examples that work better in one than the other example. So what we can now do is again create a scatter plot and have the queries now as our let's say identifiers, and now all the different metrics per pipeline as the columns in our data frame. And when we create a scatter plot for that, we can now see on the x-axis here we have the neural heavy approach, so keywordness of 0.1 and a neuralness of 0.9. And on the y-axis we have a keywordness of 0.9 and a neuralness of 0.1. And when we have a look at, for example, the top queries here, let's pick this one. We have the query pop socket mirror, And this now has, for the keyword heavy pipeline, a DCG of 13.8. And for the very neurosearch heavy one, we have a DCG of 0. So in this case, we have a clear winner for the very keyword heavy approach versus the neural heavy approach. So this view now, although there are like maybe slightly linear correlated points in here, the higher score we have in one case, the higher we also score in the other case of the search configuration, but there are clear outliers here. And what this view, or when hovering over the points, what this also gives us is we also sometimes at least can see the reason why these pipelines score as differently. And we see that when we have a look at the ratio of ratings. So the ratio of ratings for the keyword heavy configuration is 0.7, meaning that we have 7 out of 10 judged documents, query document pairs. And for the neural search heavy search configuration, we have 0 ratings. So this cannot win over the other one because we have as huge gaps as we already have pointed out in previous notebooks. So this is a very interesting visualization and it gives us additional insights that we can then further use to, let's say, refine the process that we came up with. So when looking at specific queries, we can also have a look at the different returned results and what the different ratings were for these results. So this is just now a tabular view of what we had a look at previously. And we can also have a look at yet different metrics, so the Jacquard metric that tells us how different result sets are. And we can compare 100 of the results here, so not only the top 10, but the top 100. And if we do that for the given query of pop socket mirror, and with the 2 pipelines that we already peeked into, we see that the results overall are not that different. So the top 100 results have a Jacquard index of 0.8, which is fairly similar, but the ordering then has to be very different because we don't really have a lot of shared information in the top 10 because we've seen 7 judged documents for one pipeline versus 0 judged documents for the other pipeline among the top 10. So the top 10 are more distinct than the top 100 altogether. Not surprising. We can do that for every query, calculate the Jacquard metrics here. And then we see we have now sorted even by Jacquard in ascending order. We have result sets that look very different among the top 100 if we have a look at the single query. So the query iPhones has no shared document among the top 100. The query champion for boys with a Jacquard of 0.015228, also very small overlap between the two. So this gives us a very clear idea that the 2 different configurations, they behave very differently. So this is what we would expect. And this is now something we can further explore. So unfortunately, we don't have like scores of the subqueries, meaning the keyword score within the hybrid search and the neural search score within the hybrid search. So what we can do is we can manually look at the query results and interpret the differences when looking at these results. So when we have this query iPhones here, so this is now the one with least shared information among the top 10, we can say, okay, a query is iPhones. We have that here in the keyword query and here the neural query. And then we can use the pipeline L2 arithmetic mean 0.1. Of course, you need to create this pipeline up front. We have created all of them as part of a different result set, or experiment is a better way of saying so. So if you don't have these pipelines, just go ahead and create them. You have all the information always in the pipeline name, and you know how to create these pipelines from notebook number 4 that creates one for you. So applying these accordingly shouldn't be an issue. And if we now have a look at the neural search heavy approach here, so let's execute that real quick. And then we can see, okay, for the query iPhones, we see now here, what's that? iPhone 6 case. Yeah, for the query iPhones, maybe not that bad. Yeah, it's maybe not the best result that we could expect, but still has something to do with iPhones, right? Next one again, phone armbands. Well, now you have something that is compatible, maybe with Apple at least products. So in that case, iPhone. Yeah, not bad. So again, yeah, not really iPhones, but iPhone related. Next one, product title, again, a wireless charger compatible for iPhones. Yeah, so again, maybe that would not be a 0, but maybe it would be a 1 because all of these are compatible products, right? So now we can have a look at, of course, more of these. Yeah, let's execute the same query, but with the keyword heavy weight applied. And if we have a look at these results, we see that first one, again, case for iPhones, so not that different actually. Yeah, so again, case for iPhones, and next one, again, case for iPhones. Yeah, so by looking at the first 3 results from the type of results returned, not that different, yeah, and somewhat related, but we see in terms of the specific product IDs, they are different because we have calculated the Jacquard index, and that was 0 for the 2 sets. Yeah, so again, something that is measurable for us, and that gives us an idea of how much a result set would change when switching from one to the other. What we can also have a look at is here we can compare it with the baseline, so without any neural search, and see what we retrieve here. So let's have a look at here. That looks very familiar. Yeah? So that looks very much like the top result that we also had for the 0.9 keyword heavy approach here. And that's not really surprising, right? So we would assume that the keyword heavy approach maybe shares a lot of products, a lot of returned results, excuse me, a lot of returned results with the keyword only search configuration. So that doesn't really come as a surprise here maybe, but that's a way of how we can dive into some of the details and get a feeling for how does this maybe work internally without having a look at very concrete numbers here, but having a look at concrete result sets. So let's call that a helper notebook for you to identify maybe interesting differences between one or the other approach, ability to dive into single queries and then surface some insights here. Next, we introduce a completely fresh idea of optimizing hybrid search queries. So, as already promised, we are now turning from the static approach of the global hybrid search optimization notebook towards a more dynamic approach. Our aim is to find a solution that on a per query basis can decide how much neuralness, so how much neural search weight a hybrid query should get, and how much keyword weight accordingly or correspondingly a query should get. We explore feature engineering and model training in this notebook. So we came up with a bunch of features that we thought may be helpful to decide if a query should have a higher neural search weight or a higher keyword search weight. And with that, let's dive into this notebook. Again, I ran all the steps up front to, let's say, skip the lengthy model training sections specifically. If you run through this notebook, just go so in your own pace, and of course in the pace of the machine you're working on. And we start with reading the data that we have generated in one of the last notebooks. So what we are using now is the calculated metrics per query of the global hybrid search optimization runs. What we use is we use NDCG as our proxy in that case to define when was a search result a good search result. So by doing that, I mean we identify for each query the best NDCG value and look at which pipeline scored this best NDCG value. And by doing so, we know how much neural search weight this query got. So we then have the query, we have the best NDCG value, and we have the what we call neuralness afterwards. So let's have a look at how this works. As I said, we import the calculated metrics from the previous notebooks, and what we have as a result is we have all the queries that ran for all the pipelines and the NDCG metrics, of course also the DCG metrics, but we're focusing on NDCG in that case. We are using and storing or filtering to those maximum NDCG values. So what we have as a result is for each of the queries in our training and test data set, we have the pipeline that scored best and the corresponding NDCG value. So for 250 queries, we know what was the appropriate keyword weight, and we derive the neural search weight in the next cell here. So we just say 1 minus the keyword weight that we can extract from the pipeline name that we have in the data frame. So as a result, as a, let's say, cleaned data frame, we now have the query string, we have the best NDCG value. Note that we have very small ones as well in here. And then we have the corresponding neuralness. So again, that we have as few judgments as we have already noted, it is an issue that comes with some uncertainty to this approach. What we have defined now is a certain amount of features that we can now engineer. So we divide them into query features, keyword search result features, and neural search result features. Let's start with the query features. Query features we have 4. The first one is num of terms. So that is the number of query terms that we have in a query. So if we have a query Apple iPhone, that would have 2 for a number of query terms. If we had red Apple iPhone, that would be 3 query terms. Next we have query length. Similar to number of query terms, but in this case we're counting the number of characters and not the number of terms. So a longer query will have more characters, so a higher, larger number of characters. Has numbers, so that is just a 0 or a 1. A 1 if it has numbers, the query has numbers, 1 at least, or a 0 if there are no numbers. Next, fourth position, we have has special character. So accordingly or similarly to the has numbers feature, if we have a special character in the query, this will be a 1. If we don't have any special characters in the query, this will be a 0. We have the definitions of these functions that do the feature engineering for us. So for each query, we can then apply these functions, which gives us an intermediate data frame that looks like the following here. For each query string, we have still the corresponding NDCG and neuralness values. And then we have the number of terms the query length in characters, if the query contains numbers, and if the query contains any special characters. That's the first feature group. The second feature group, keyword result features and neural search result features. For the keyword search result features, we have three. We have the number of results for this keyword search query. So without any neural search, how many results did the keyword search query retrieve? We have the maximum doc score. So we have a look at the BM25 scores per query per title within the top 10 documents retrieved. We are using the Python library search array here, and we calculate the BM25 scores really individually per result set. So this means we are not taking any OpenSearch calculated scores. We are calculating individual scores per result set, per query title pair. We'll see that in a minute when we have a look at the function. We take the maximum score as feature number 2 within this keyword search result feature group, and we also take the sum of all 10 title scores. So the first one tells us how well did the best document score for the title, and the second feature, the sum of doc scores feature, tells us how well is the whole result set working for this query. And then we have two neural search result features, and we use the semantic scores for that. So we measure or retrieve the semantic scores for the neural query for the top 10, and we take the maximum again, so what is the best score, and we take the mean of the 10 best title scores for that. So that is feature number 8 and 9 then. We have 9 altogether. 4 query features, 3 keyword search result features, and 2 neural search result features. We have a couple of helper functions that we need mainly to know what is the model ID that we use. So let's get model ID. Then we have a tokenizer that is just applying whitespace tokenization and lower casing. We need that for the keyword search score calculation. And then we have a function that retrieves all the titles for the keyword matches for later score calculation. So let's apply these functions, or define the functions and then apply them. We need to retrieve the number of results, so we execute all queries, but only the keyword search results. So keyword search only, no neural search applied here, and all that we want is the number of results per query. Next, get titles for queries. So in that case, we only want to have the titles, and we store these we return these in a data frame. Again, that is only product titles, so only keyword search, no neural search applied, no other information, we only have a look at titles. Tokenizer definition, we need to split the titles that we have retrieved into tokens so that we can calculate the scores later on. And the tokenizer that we define is split on whitespace and then lower casing. We have 2 functions that calculate the maximum score and the sum of doc scores, so that is the title scores, the BM25 scores. That's where the search array library comes into play. So what we do is, for each of the titles that we have retrieved, we index these and store this in a new data frame column. And then we also tokenize the query. And then we calculate the score for each query term for the indexed title. And this means that we always look at only the 10 titles that were retrieved for each query and not more. So we don't take into account any, let's say, index-Y document frequency, which maybe introduce a bias somehow. We always look at a very narrow part to have a, let's call it a way of normalizing this calculation for us. The sum of doc scores has more or less the same calculation, but what we're using is we're not using the maximum of these calculated scores per title, but we are using the sum of all these title scores. The semantic scores is again quite easy because we can use OpenSearch for these, so we retrieve all the semantic scores and store them as a feature. So we apply these functions next, and that has as a result a data frame with, for each query, now all the different features that we have defined. So new now are number of results, the maximum title score, sum of all title scores, the maximum semantic score, and the average semantic score. Now that we have all our features, we can look into training a model. So what we did is we did experiments with two model types, linear regression model and random forest regression model. So we ran a lot of different combinations. So we applied cross-validation to have, let's say, a statistically sound process. We also tried out different feature combinations. We added regularization, and the different notebook cells take you through these different experiments that we did. So I won't go into all of the details here, but explain the cells briefly. So the first one here is, let's call it the simplest one. So we are training a linear regression model. We are applying cross-validation, and we want to know what is the best feature combination. So feature combination can be, we train a linear regression model with feature 1 and 2, with feature 1 and 3, 1 and 4, and so on. So all different combinations for our 9 features. And then we want to know what is the best one out of these combinations. So that gives us an idea of how useful the different features are for the different types of models that we are looking into. And if we try out all these different feature combinations, apply cross-validation again, I'm skipping over the code here. We're looking at the root mean squared error, and that gives us a best feature set of feature 1, 5, 7, and 9, and that is the number of terms, so one query feature, the number of results, the sum of all title scores, so 2 keyword search result features, and then the average semantic score. So it looks like we're not able to, let's say, focus on only one feature group, but have to use features from the different groups. We also ran this approach for more data, so not only the 200 or 250 queries, but for 5,000 or 80% of 5,000 queries. And the feature combinations there are longer ones, actually. Yeah, so when using smaller data sets, smaller or fewer combinations, or combinations with fewer features is a better way of explaining it, are the result here. So you definitely have to explore this on your data set should you choose to really apply this approach to your setting. That is one of the main messages here. Next, we do the same, but apply regularization as a means to prevent overfitting. So in this case, we are more or less just switching the linear model and apply L2 regularization. We try out different alpha values for this regularization, and what we have seen here is if we use more data, regularization does not help us. So if we go from the 250 queries query set to the 5,000 queries query set, regularization hurts. But if we have fewer data points in our training set, so the 250 query set, we need regularization to achieve better results. And we can see that by reporting the highest alpha that we try out. That means when we have an alpha of 10, so applied regularization, alpha of 10, we have slightly better cross-validation scores for the feature combination of all features, right? So we did not explore regularization plus feature combinations here, but that's what we do next. So here we have regularization and the different feature combinations that we iterate over. We use the best alpha value that we have identified up front. And now we again arrive at the same feature combinations like before and have very similar overall cross-validation scores. So regularization apparently helps, but it doesn't give us like a huge boost. But at least when we have a look at fewer data points, it does help when we look at the numbers that we receive here. So in summary, feature combination of these 4 features and an alpha of 10 by applying regularization is like the best combination that we explored when looking at the small data set. Next, random forest. So random forest, we did the same steps. So cross-validation and feature combinations, then apply regularization, and then we combine both. So let me show you the numbers. The best feature combination here features F2, query length, F3 has numbers, F4 has special characters, F5 num results, and F7 sum of all title scores. So interestingly here, no neural search result features apparently for the best combination here. We also see that the best cross-validation score here, the best root mean squared error score here is 0.27, which is higher than the best linear model score. So linear model slightly better in performance when looking at the first exploration of random forest regression here. Next, we have a look at regularization. So that's a randomized search that we apply here, searching over a couple of different parameters that we can define for training a random forest. So it's basically a way of tuning hyperparameters. And again, not iterating through all the code here, giving you the summary. Here, actually, we only have 2 features as the best combination that comes out of that. So has special characters and the number of results. And we have a best parameter set of, we have 50 as n estimators. We have a min sample split of 2, a min sample leaf split of 4, and max features of log 2 and a maximum depth of our tree of 3. If you want to read up all these parameters, they are well documented in the scikit-learn documentation. And now we see better performance than the best linear model. So this gives us, again, better performance, which is what we are after. So the best trained model according to the small data set that we have here is the random forest regression model with these parameters that we are seeing here and the 2 features in combination. Next, we can have a look at how the different cross-validation runs, how they scored, and we can do some visualizations to see what is the spread of the different combinations to get a feeling of how certain are these results that we are looking at. And if we calculate a couple of, let's say, statistics here, let's move to the first visualization. This is now a plot that shows us for the best feature combinations across the linear model and the random forest models, with and without regularization. What is, let's say, the spread in these box plots within the individual cross-validation runs. So what does that mean? If I have a look at the first one here, we see that this is the combination of the second feature and the fifth feature, so query length and number of results. That may be the best, let's say, option, the random forest option. It's likely that it is that one. And we see that we have a minimum and a maximum, and they are pretty far from each other. Yeah? So the minimum of 0.23 and the maximum of 0.31 means that we have quite a large spread. And this now lets us think that when we have a look at only very small data sets and train models on these, we have high uncertainty. And if we only have a look at two features, this kind of makes sense. So we would maybe expect even the larger spread. And as we have a very low minimum here and probably more values in the lower half of what we are seeing here in the bar plot, box plot, that will lead to this. That will lead us to this lowest mean value that was reported. And we see that sometimes the spread is maybe slightly lower, like for this combination where we're looking at 4 features, where we have like from minimum to maximum only 0.065 roughly, versus here almost 0.08. So different feature combinations, different spread in root mean squared errors within the 5 cross-validation runs for the experiments. We can dive into the individual model types. So here we see the same box plot, but only looking at linear regression models. And we see again the same visualization type, but for the random forest option. And again, we can do the math and, for example, say the spread for the first one doesn't look that large, 0.34 to 0.29, which is basically 0.234, 0.291, which is like 0.57, 0.057, sorry, and can pick a good one for the random forest option, 0.227, 0.9298. So similar range, roughly at least, yeah, and that gives us an idea of the spread is seemingly comparable when we look at linear models and random forest models. We can also dive into the aggregated metrics, so not look within the different cross-validation runs, but rather aggregate over all these runs and then have one metric, one root mean squared error per feature combination. And we can also have a look at different feature combinations, so combinations by feature types. So in this case we have a keyword, result feature and query feature combination. And we have combinations of all the other ones. Yeah? So K is a keyword search result feature, N is a neural search result feature, and Q is a query feature. So different combinations of the different types lead us to different performances of the models when we use these as training data feature input sets. And maybe more interestingly, if we have a look at, let's say, homogeneous feature type groups or feature groups. So the purple or purple bluish ones on the left-hand side, they are query features only. The red ones are keyword search result features only. Green one is neural search result features only. And then here the purple ones, they are on the right. They are combinations of the different types. And what we can see is that the combinations score better. So apparently that one here specifically score better than the other ones, and looking at individual ones also gives you, at least not always, but sometimes a wider spread. Specifically here, the neural features only, they have like the widest spread of all. Again, here looking at in this case, the neural models only. Looking at, that is now the random forest ones. We have unfortunately different color coding, so no neural search result combination, because that's not among the top 10 apparently. But here again, widespread actually for keyword and neural search result features. Lower spread for query and keyword result features. And always when we add like the neural search result features, it seems that the spread grows for the random forest combinations that we look into here. Also maybe interesting that the medians that we are seeing for keyword and query result features, they appear to be on average at least lower than when we have neural search result features in the mix. Again, for this small data set. Here, if we have the, again, homogeneous groups, it looks slightly different, or maybe, let's say, more interesting. If we have query features only, these look like not so good box plotted values here. So the green ones, so only keyword search result features, they seemingly outperform the others, but also the keyword and query mix here, that seems to perform really well. The neural features again have the widest spread. And mixing all of them makes it again at least competitive. At least the minimum that was reached here is very competitive to the other combinations. So again, depending on the cross validations that we are looking at and also the amount of data that we are using, we can see different pictures. If you want to dive into a couple of these diagrams for the larger data set, look at one of the past issues, that is issue number 1 in the hybrid search optimizer repository. You can see a couple of diagrams there, or just run the 5000 query set yourself. So glancing over the next couple of visualizations, we now come to the actual model training part. So now that we know what are the features that apparently work best, what is the best alpha, what are the best hyperparameter settings that we can apply, we can set these, we can train models, again using only the queries from our training set to train and of our test set to test everything. So 200 queries training, 50 queries test, but the same ones as in the previous notebooks. And we train the models, linear regression model with regularization applied, and here a random forest model, again regularization applied and the best feature combination. We can then save these models, and last but not least, we can run the queries of the test set to calculate metrics for the 50 test queries and then compare that to the baseline and also the best hybrid search parameter combination that we identified. So let's get into the last notebook. What we do is we first load the models that we have trained in the previous notebook. We can have a look at, can actually execute all of these right now. We can have a look at what are these models, so to know are they really the ones that we just trained. So yeah, we had an alpha of 10 as the best one, and this ridge model is linear regression with regularization applied. Here we have the random forest regressor with the also known parameter set. We next load the query set that is now our test set, so the 50 queries. We of course need the judgments again. We can have a look, is it really the 50 queries containing, or the data frame with the 50 queries from our data set that we use for testing. Looks good. We can have a look at what are the features. So these are the ones that we have actually used to train our models. And then we can make predictions for the queries. So what does that mean? We now take the data set, the test data set, and we already have all the features calculated because we did that in the previous notebook. So we calculated the features for all 250 queries, but then left out the 50 in the training part. So we don't have to recalculate them, but what we can do now with all the features that we already have calculated, we can make the predictions with the trained models. So for each of the queries with the features, we can now ask the models to make a prediction based on that. And that then gives us the predictions in terms of, we now have a prediction for the linear model and we have a prediction for the random forest model. And this prediction now is a dynamic way of saying how much neural query weight do we want to apply. And with that information, we can now actually run these queries, right? So we can now execute this query for every one of the 50 queries. So for every query and for every model, so that means we have a linear model and the random forest model, we can get the neuralness value out of our data frame, apply this neuralness value in the query. We can use the neuralness value to also arrive at the keywordness value. And what we have set here as our defaults is actually the L2 normalization technique and the arithmetic mean technique, because they looked best when we had this best hybrid search configuration experiment where we did the global hybrid search optimizer. So that's why we use these two as the default and just have the dynamic prediction of the keywordness and the neuralness of a query really applied here. We retrieve 100 results, again stored in a data frame, and then we know for every query what was the neuralness that we actually applied, and what was the model type. And what we do now, again, what we already know, what we've done a couple of times right now, is we get the ratings, merge the ratings into our data frame with retrieved documents. And you can see here again already known gap of some of the ratings. Forgot to execute a couple of cells here. And we can have a look at how many of the query document pairs, where do we have actually ratings. And we see again large gaps here, so roughly 90% gaps, more than 90% gaps. And among the top 10 it looks slightly better, so that's again this 32% where we actually have the ratings, or 67.5% where we are missing the ratings. And now we can calculate the metrics again with the same formulas that we have imported in the other notebooks. Again, DCG and DCG precision. And that gives us for our test data set for each model, for each query, a DCG value, a NDCG value, a precision value. We can have a look at the different result sets here. So result sets in terms of, for one query, in this case, something for suing at least. There we see the top 10 retrieved results. We have ratings for some of them, not all. And now we can average over the calculated metrics. So if we average over the linear model queries, we get these averages here, 6.11 for DCG, 0.27 for NDCG, 0.31 for precision. And for the random forest one, we get 6.3 as a DCG value, 0.28 as a NDCG value, and 0.32 as a precision value. And if we now take these and add it to the table that we started building out when we first ran our baseline search, we can now see. We already know that we improved baseline by applying the global hybrid search optimizer, right? So here's our baseline scores, baseline metrics. Here's what the global hybrid search optimizer gave us. Here's now what the linear model gave us, and we see it's actually not performing better than the global hybrid search optimizer, so slightly worse metrics here. But interestingly, the random forest model outperforms the previous runs. So now we have improvements across all metrics. So we have a higher DCG value, we have a higher NDCG value, and we have a higher precision value compared to the baseline. Only the precision value does not improve when looking at the global hybrid search optimizer, but the other metrics do. So this is very promising, even when looking at this very small data set. We even saw improvements for the linear model when we explored larger data sets to train on. So if you rerun everything with the large query data set, you should see these improvements as well, with different feature combinations, of course, but the overall approach is the same, and the metrics improve from baseline to global hybrid search optimizer to the model-based or model-driven approaches here. The last couple of cells give you the chance to dive into a couple of the specifics. So having a look at individual queries is what we can do here. And when I scroll down to one of the visualizations here, we can see that when we have a look at the DCG values of the linear model and the random forest model, we actually see a couple that outperform for the random forest model, which is maybe expected because the random forest model slightly outperformed the linear model. Also, when we look at the NDCG values, it is the same picture, but apart from that, good queries in one case also perform well in the other case. So high performers linear model, also high performers random forest model, but there are differences, of course. Looking at these differences, we can now calculate the difference between the DCG values, and that gives us an idea of where they differ. And looking at only 50 queries, we can see that there are not that many differences. So only a couple perform differently. So after position 5 here, we have equal DCG and NDCG values. So the differences are marginal, and it will be interesting to further analyze this approach and see how the picture changes when actually having maybe a more complete data set. But in conclusion, what we can see here is that we picked up something here, and we can apply this very straightforward and very naive approach of just trying out predefined combinations in a, let's call it, brute force way. But we can further improve on that when we dynamically train on generated data by the global hybrid search optimizer and find nuances when to go in one direction and the other direction. So that's basically the run-through, the walkthrough through the notebook set of the hybrid search optimizer. Please provide feedback. We'd be happy to receive that and further improve that based maybe on your individual findings.